Okay, so think of your FortiGate as way more than just a firewall. It's actually the ultimate traffic hop of your entire network. I mean, every single packet of data that arrives at its doorstep needs immediate direction, right? So today, we're going to peel back the layers of the FortiOS internal routing logic to understand exactly how those split-second decisions are made. Picture this real-world scenario for a second. You've got thousands of packets hitting your network every single second. How in the world does your router instantly know the difference between someone streaming Netflix and, say, a critical database syncing with AWS? And more importantly, how does it know to route them down completely different internet paths without even breaking a sweat? Well, that's the puzzle of dynamic internet routing that we're going to solve in this explainer. So here's our game plan. We're going to cover the core routing principles, dive into the route lookup process, figure out breaking routing ties, explore internet services routing, touch on reverse path forwarding, and finally wrap up with ECMP and load balancing.
All right, let's kick things off with Section 1, Core Routing Principles. Now, when operating in its default NAT mode, FortiGate functions as a full-fledged IP router. It has to figure out the next hop for two distinct types of traffic. Firewall traffic, that's passing directly through the unit, and local out traffic, which is generated by the FortiGate itself. To do this at blistering speeds, it actually uses two different versions of the map. First up, there's the RIB, or Routing Information Base. This is your standard routing table. It's the map you see as an administrator when you're looking at the GUI. But then there's the FIB, the Forwarding Information Base. This is the map from the kernel's perspective. It's stripped down and perfectly optimized for split-second hardware lookups. So when FortiGate actually performs a route lookup, it queries this hyperfast kernel-level FIB.
And here's where it gets really interesting and surprisingly efficient. The FortiGate doesn't actually check the map for every single packet. No way. For any new session, it evaluates the routing table exactly twice, just twice. Once for the first packet sent by the originator, and once for the very first reply from the responder. After that, it just writes that routing information directly into its session table. All the subsequent packets in that session just follow the session table, completely bypassing the routing table altogether. Unless, of course, some major network change forces a hard recalculation. Moving right along to Section 2, the route lookup process. You know, it's a strict rule of network architecture that routing decisions have to happen before most security features. Your security policies rely entirely on the outgoing interface that's selected by the routing engine. And to make that decision, the FortiGate uses a very strict top-down funnel. First, it checks regular policy routes. If there's no match there, it checks the Internet Service Database and SD-WAN rules. Still nothing? Okay, it checks the route cache. And finally, it checks the FIB, that kernel routing table we were just talking about. If a packet makes it all the way to the bottom without finding a matching route, it's just dropped and an unreachable message gets sent back to the sender. It's a highly logical, completely top-down process.
All right, on to Section 3, Breaking Routing Ties.
But what happens when that nice, neat funnel gets messy? In complex networks, it's incredibly common to have multiple paths that all lead to the exact same destination. So if the router has 3 different routes, all claiming to be the absolute best way to reach a destination IP, how does it break the tie? Well, it relies on a very specific hierarchy of attributes. The absolute first tiebreaker is administrative distance, or AD. Think of this as basically the trustworthiness of the route's source. The lower the distance, the higher the preference. So a directly connected route has a distance of 0, effortlessly beating a manually configured static route at 10, which in turn easily beats an OSPF dynamic route sitting at 110. The route with the lowest distance gets installed in the active routing table, and the others just become standby routes. And hey, here's a pro tip that might literally save your weekend. Never configure different routing protocols with identical distances. If you do, FortiGate just keeps whichever route arrived last, which makes your network highly unpredictable. Okay, but what happens when the colliding routes come from the exact same protocol? Let's say you've got 2 OSPF routes tied at a distance of 110. Well, that is where metrics step in. Metrics are intra-protocol tiebreakers. So for OSPF, the metric is cost, which is based on bandwidth. For RIP, it's the hop count. And the rule stays the same. The lower metric wins and gets installed in the routing table. Now, if you're dealing strictly with static routes, there's one final tiebreaker in the arsenal, and that's priority. If 2 static routes share the exact same distance, FortiGate actually installs both of them into the routing table. To break the tie during the lookup process, it looks at the priority setting. The default value here is 1, and just like distance and metrics, the lowest priority number wins the right-of-way.
That takes us to Section 4, Internet Services Routing. Which brings us perfectly back to that opening puzzle. We know how routing works and how ties are broken, sure, but how do we handle massive, dynamic, public IPs for modern cloud services? Traditionally, we'd use a default route, the famous 0.0.0.0, to just send all unknown traffic to our ISP. But if you want to route Netflix traffic out of ISP1 and AWS traffic out of ISP2, traditional static routes are an absolute nightmare. I mean, you'd have to manually track down thousands of IP addresses for these services, create static routes for every single one of them, and then constantly monitor them for changes.
Enter the Internet Service Database, or ISDB. The ISDB acts like a dynamic VIP lane. Fortinet constantly updates this massive database of IPs associated with major internet services. So you simply apply the Amazon AWS object directly to your static route. Now, here is the real secret. Even though you configure this in the static route menu, ISDB routes actually function as policy routes. They get injected into the policy routing table, meaning they take top priority over standard routing. Netflix goes exactly where you want it to, instantly, without you lifting a finger. Pretty cool, right?
Next up is Section 5, Reverse Path Forwarding.
Because, as we know, routing isn't just about moving packets forward. It's also a vital security checkpoint. Reverse path forwarding, or RPF, actively protects your network from IP spoofing attacks. When a packet arrives, FortiGate checks to see if it actually has a valid route back to the packet's source address through that specific incoming interface. By default, it uses feasible path mode, which means as long as any matching return route exists, the packet is allowed. But in strict mode, the matching return route must be the absolute best active route in the routing table. Otherwise, the packet gets dropped as a suspected spoof. And remember our golden rule of efficiency? This security check is only performed on the very first packet of a session.
Finally, let's jump into Section 6, ECMP and load balancing.
Let's explore the multi-lane highway. What happens when routes are perfectly equal and we actually want to use all of them simultaneously? Well, when multiple routes to the same destination share the exact same type, distance, metric, and priority, they become equal-cost multipath, or ECMP routes. FortiGate installs all of them and actively balances the load, and it can do this in 4 different ways. Based on the source IP, based on the source-destination IP pair, using a weighted system where you give a higher percentage of traffic to a stronger link, or using a usage spillover, where it fills up one link's bandwidth entirely before spilling over into the next one.
And here is the real beauty of ECMP. Built-in failover. Say user A is routed out of port 1 and user B is routed out of port 2. If the connection on port 1 suddenly drops and gets removed from the routing table, FortiGate instantly and automatically reroutes user A's traffic right over to the remaining active port 2. It provides high availability and bandwidth aggregation without any complex scripting on your part.
So, ECMP is an incredibly powerful tool for utilizing multiple WAN links. But it does beg a really fascinating final question. What if you could take that foundation, strip away the static load balancing, and add highly intelligent volume-based application steering right on top of it? By simply enabling SD-WAN, FortiOS replaces standard ECMP with an advanced load balance mode, opening up a whole new world of dynamic traffic shaping. But are you ready to hand the steering wheel entirely over to SD-WAN? Well, that is a topic for our next deep dive.